I'm going to start discussing analytical mechanics. I call it Lagrangian mechanics. Now, it's a different way of looking at classical mechanics as opposed to the mechanics of Isaac Newton, where you use force equals mass times acceleration and usually vectors. I do have lectures 1, 2, and 3 giving you the basics of this stuff, which comes out of the calculus of variations. Important person in the calculus of variations is Maupertuis and also Leonhard Euler. Also William Rowan Hamilton, actually. I'll go through those guys in a minute. Now, what else can I say? It's a much more, this is lesson number 3. It's a much more sophisticated and naturally beautiful way of looking at mechanics than the other ways of looking at it, okay? We use generalized coordinates. What are they? They are coordinates set up to match the system that you're looking at. For example, if a particle is constrained to move on the hoop of a circle, a generalized coordinate would just be the angle that it sweeps out. That's all. Because if the radius is constant, that's not a degree of freedom. The number of generalized coordinates, and we'll call the generalized coordinates qi, where I is equal to 1 to n. N is the number of degrees of freedom of this system. If a particle was constrained to move on a circle, but not so much on a circle, but in a plane, let's say executing motion around a planet, there would be 2 degrees of freedom, the radial motion and the motion in the plane. An angle and a radius, right? Polar coordinates would do for that, but the generalized coordinates could be labeled as such. Generalized coordinates can in fact be Cartesian coordinates or polar coordinates or sphericals or anything that you choose to be, such as the length of a pendulum if it was changing. Okay, so let's do some people. Giuseppe Lodovicio, he was from Turin, but he died in Paris where he mostly worked. His name became Lagrange, Joe Louis Lagrange, Lagrange's equation. But a lot of people did work on this. Maupertuis had done a lot by the time this guy got started. Maupertuis from Saint-Malo in France, one of the towns favored by my great friend John Quinn, who fought in World War II and spent some time there. He was a great guy, John Quinn. I'll tell you about him someday. William Rowan Hamilton. I fell into his tomb when I was about 10 years of age because I didn't know he was a famous guy until even quite recently. Even though I learned about him at London University in the 80s, I didn't know he came from my town, the village that I grew up in. The family home is still there. It's called Hemwood Stud, okay? William Rowan Hamilton did a huge amount of stuff. Quaternions, Hamilton's equations, the principle of least action, many, many things. That's him. Leonhard Euler, calculus of variations. The equation here, I didn't write it on the board yet. The Lagrange equation is also called the Euler-Lagrange equation. I call it the Lagrange equation. He gets the credit for it. Okay, so basically what we're talking about here is a thing called the action. The action is the difference between kinetic and potential energy. And there'll be coordinates in here and their derivatives, okay? Now sometimes an action can depend explicitly on time, and there's a certain name for that type of an action. Otherwise it's not an explicit dependence on time. You can look up the terminology yourselves. I don't bother with the terminology people get. When people say rheonomic and scleronomic, they start tripping over themselves. The way we're going to learn this is, I will start doing examples for you. I will go back later on in lesson number 1 and do some calculus of variations and derive the Euler-Lagrange equation from first principles. It's a bit of a mess. However, today I'm just going to tell you this, that particles, classical particles, do a miraculous thing. Particles move on a path such that it is an extremum. In other words, it could be a minimum. That means nature uses up the least amount of energy. A soap bubble is an example of that, okay? The way a chain hangs, it's a catenary, hangs in such a way that the action, the potential energy is a minimum. That's different. That's not motion. That's statics. Okay. So the action we'll call the action is called S, and it's this integral. It's a function of whatever that is. And L is a function of the coordinates and their derivatives, the difference between the kinetic and potential energy. Qi are the generalized coordinates. Degrees of freedom. Qi dot is a derivative of a Qi. Now the condition that S is an extremum is given by Lagrange's equation. In other words, here's a path. But we want, that's a big long path. We want the shortest path between 2 points, right? There are many examples we'll talk about. Fermat's principle. There's a whole lot of stuff in here that we'll do in lectures 1 and 2. Maybe 4 as well. But today we're just going to learn how to use this to solve problems. If you're a student, this is how you'll do it, right? You'll get problems like this. Set up the Lagrangian and find the equations of motion. The problem is always the same. The situation is different. Okay, the condition that S is an extremum or a minimum is Lagrange's equation. I'm calling the generalized coordinates Qi's actually. Now, this is the basic equation. In different circumstances, we can introduce constraints. We're not going to do that today. That's subject for a second lesson. When we have constraints, they are equivalent to generalized forces. This here will usually give me an equation of motion such as something like that, some other bunch of parameters. In other words, the second derivative of the coordinates is some other function of them. Okay? So far so good. Let's do an example, or a couple. We're just going to take standard examples. I'm going to clean the board now. You've got all of this. Now I should get my clock. That's about 10 minutes. Because I get half an hour or less for all of these. Now we'll use this equation to work for conservative forces. What does that mean? It means that the forces can be derived from a potential. Okay? So let's see what happens. Let's think of an example. Example number 1, the simple pendulum. Now this is just a simple pendulum. We can also do a compound pendulum, and that's the way we will work. We will do a compound pendulum eventually. That's one pendulum followed by another one. A simple pendulum just looks like this. It has a string of length L and a mass of length M on the bottom. And it's free to swing, so therefore it sweeps out a certain angle. We will measure that angle theta from the 0 point. Now when the pendulum swings, it also goes up a certain height. Let's exaggerate that. There's a height h, and here's a triangle, and here's the length L, and this is theta. H is L cos theta, not quite. It's L minus L cos sine theta. There's L, and here's L cos theta. Is that right? No, here's L cos theta. And here's L. So this little height here is L minus L cosine theta. So let's apply Lagrange's equation to this. Now in this case here, when the pendulum is swinging, there is only 1 degree of freedom. This is not a degree of freedom. The degree of freedom is angular only, because the string length is kept constant. So theta is our only generalized coordinate. So we apply Lagrange's equation, d by dt, dl by d theta dot minus dl by d theta equals 0. Well, the kinetic energy, the T, is a half mv squared as usual. Well, the strain, well, you know, if you have a R and theta, the speed is the derivative of R theta, and if R is a constant, it's just R times d theta by dt. So R theta dot is R times d theta by dt, but R is replaced by L, so that is the kinetic energy. Okay, so far so good. Now we need the potential energy. Well, V is mgh. It's always mgh. Well, I just worked out what the h was. It's mgl minus L cos theta. Now we go d by dt, sorry. First of all, we write down what the L is. Make sure I'm doing this right. Okay. So that's what we've got. Now we don't need this board space anymore, you've seen the idea, because I want this for my calculations. So now we just go d by dt, now dl by d theta dot, okay? Is the derivative of that term there, where we're taking derivative with respect to theta dot. And that's what it is. So the two cancels. And our d by the theta, sorry, theta double dot is just the derivative of the theta dot, d squared by the theta by dt squared. Okay, so that's what dl by dt is. So d by dt of this thing here is d by dt of no, I made a mistake. It stops at this. No double dot yet. Made a mistake. The double dot comes in down here. That's where the double dot comes in. And that will generate our forces. Now minus the negative dl by dt, d theta. the L by d theta is the derivative with respect to theta only. So there's no derivative with respect to L is going away, that's a constant. And we just go, take the derivative of this term here and keep the constant and the m and the g. Now don't forget the minus sign. So now we have a result. For this particular case here, we get ml squared plus and that's the equation of motion. Now the equals 0, of course, the m cancels and one factor of L squared L cancels. Now I hope I have my signs right here. Well, I'll check it later. Now, that's the equation of motion. For small oscillations, I want to check my sign later. That theta is small, sine theta is almost theta. And we get the usual result, okay? Simple harmonic motion. Where omega squared is g over L, and t, or the period, now I made a mistake, that's 2 pi root L over g. So we get the usual result when theta, sine theta is small. Now when theta is not small, this has a very interesting solution. It's nonlinear. And it leads up to the idea of chaotic motion. But we'll talk about that in another example. Our next example is going to be masses on a spring. Today was just beginning. Okay? There's more great stuff to come. It's the way to handle stuff. If you can get your control over this, Lagrange's equation, you'll be able to solve very tricky problems in mechanics. But it's also lovely to see the way nature works, because force equals mass acceleration doesn't really tell you why, what nature is doing. Nature is moving such that the action is a minimum. That's the way nature likes to work. The planets go round the sun in orbits such that the difference between the potential and kinetic energy is a minimum.